Where did we end up last time? So last time we defined the Dane function. We said that if x is simply connected a simplicial complex or manifold then we defined the filling area of a curve to be the infimal area of a disk beta, where beta has boundary equal to gamma. And we defined the filling area function of x to be the supremal filling area of curves gamma, such that the length of gamma is less than L. And we said that if G acts geometrically on x and y, where x and y are simply connected simplicial complexes or manifolds, then the filling area function of x and the filling area function of y grow at the same rate, where grow at the same rate meant that they satisfy some equivalence relation, that there exists some c greater than 0 such that the filling area function of x was at most c times the filling area function of y, evaluated at cl plus c plus cl plus c, and likewise for the filling area function of y. And this is an equivalence relation so usually we say that the filling area function of x and the filling area function of y grow at the same rate. So this is an equivalence relation that distinguishes, say, different polynomial orders of growth as long as the degree of the polynomial is at least 1. It distinguishes polynomial from exponential, but it doesn't distinguish different exponential rates of growth because, well, we've got this linear factor inside the argument. So we can't tell the difference between 2 to the x and e to the x. But we can tell the difference between x squared and x to the 2.1. So yeah, so what I want to do today, I would like to talk about some examples of groups and their Dane functions, and in particular, I want to talk about a particular example of two solvable groups that are very similar but have very different Dane functions, and talk about why that is. So talk about the geometry that makes that happen. So let's start. So let me just first note that because of this theorem, because the filling area function of a space just depends on the group that acts on that space, that means we can define the Dane function of a group let's say delta sub g of g by letting x be a space that's simply connected and g acts geometrically on x. In that case, then the growth rate of the filling area function of x is well defined, and so we can let the Dane function of the group be the filling area function of that corresponding space. So what are some examples of groups and their Dane functions? Well, there's a strong connection between the Dane function and curvature. So the classical example of a group and its Dane function is that if we let G be, say, Z2, then G acts geometrically on the plane. And the question of the maximum area bounded by a closed curve in the plane is classical. If I have a curve in the plane of length 2 pi r, then the largest amount of area that that curve can bound is if that curve is a round circle of radius r. And so the filling area function of R2 evaluated at 2 pi r is pi r squared. And so the Dane function of G is on the order of r squared. Let me write it this way. The Dane function of G of evaluated at L is on the order of L squared.
In your definition, the Dane function depends on the choice of the x?
Yes, the Dane function depends on the choice of x, but the growth rate of the Dane function, the equivalence class with respect to this equivalence relation, doesn't depend. So there are so G acts on R2, and here I've given R2 the Euclidean metric. But if I give it some other metric, the L1 metric, the L infinity metric, if I give it some other metric, it still acts. We can still define filling area, but depending on the metric I choose, the constant's going to be different. That's why we have this equivalence relation, so that we can say that the exact constant doesn't matter. What we really care about is the dependence on L. Okay? So in the plane, our Dane function is quadratic. And really, this is a consequence of the fact that the plane is non-positively curved. If x is non-positively curved, so I'm going to write k sectional curvature less than or equal to 0, then I guess I need non-positively curved and complete and simply connected. Then I have a unique geodesic between any pair of points. And so in particular, if I have a curve in x of length L, then I can construct a disk whose boundary is that curve by picking some point on the curve, drawing the geodesic from every point on the curve to that base point, and then calculating the area. Well, what's the area of the disk that's constructed in this way? Well, each of these triangles, if this segment has length 1, then this is a triangle, or at least this has the area, at most the area of the triangle with sides of length L, L, and 1. So the area of each of these wedges is at most on the order of L. And so because I can break the curve up into L wedges like this, that means that the total area is at most on the order of L squared. And so that means that if x is non-positively curved, then the filling area of x is at most on the order of L squared. Right? Is this okay so far? Yeah?
Is it easy to see that the circle is the worst case?
In the plane?
Yes.
Well, so that's classical. That's the isoperimetric problem in the plane. So it's the usual. You use the usual calculus of variations argument where you say if you have something that's not a circle, then you can draw triangles.
That doesn't give the equality PR.
Where?
You wrote FR of equal PR squared. Yes, for equivalence, I agree.
Uh-huh. Well, so the exact constant that you get depends on your choice of x. With the Euclidean metric, it's exactly this. I think you can show that if you put any norm on the plane, then this is the best constant that you can get. But I'm not. But then you have to work. But that's a different story. For what I'm doing, for what we're doing, we really don't care about the leading constant. For what we're doing, we really just care that it is quadratic, rather than, well, we'll see that depending on groups, you have linear growth rates, exponential growth rates, all depending on the group you're looking at. Is it okay? More questions? Okay. So if I have non-positive curvature, then if my space is non-positively curved, we have a quadratic, at most quadratic rate of growth. I say at most quadratic because if x is negatively curved, so again, if x is complete, simply connected, and if x is negatively curved, and let's even say pinched negative curvature, so I'm going to have the sectional curvature less than or equal to kappa, which is strictly less than 0, then we can apply the same argument, except we get better bounds. Because if we have negative curvature, then if I have 2 points that are spaced a distance 1 apart, and then I draw the geodesics from those points to some third point, then the distance between these geodesics, because of the negative curvature, the distance between these geodesics is going to decay exponentially quickly. And so this distance here is going to be on the order of e to the minus r, where r is the distance here. And so the area of this triangle is going to be on the order of 1. And so when we make this same argument, when we construct this same disk, by picking a base point on the curve and then drawing geodesics to that base point, well, we have L points on the curve spaced about 1 apart that break up this disk into L wedges like this. Each of these wedges has area at most on the order of 1, and then there are L wedges like this, and so the area of this entire disk is at most on the order of L, and so the Dane function, the filling area function of x, is at most on the order of x. Is this okay? Okay, so, and furthermore, so this says that if we have not, so if we have non-positive curvature, then it's bounded by a quadratic function. If we have negative curvature, it's bounded by a linear function. It turns out that in the case that in the case that x has negative curvature, the implication actually goes both ways. If x is negatively curved, then the filling area function of x is at most linear, and it's a theorem of Gromov's that in fact we can go the other way. That in fact, if G is a finitely presented group, then the following are equivalent. The Dane function of G is on the order of L. The Dane function of G is strictly less than quadratic. So in particular, there are no groups with Dane functions that are between linear and quadratic. If you have a group whose Dane function is bounded by, is smaller than any quadratic function, then in fact its Dane function is linear. 3, the geodesics diverge exponentially. And what this means is that if I take a point and I take two geodesics coming out of that point, and then I look at the ball of radius r around the point, then the distance between this point and this point, the distance between these two intersections where we restrict to curves that stay out of the ball of radius r. So if I look for curves that stay outside the ball of radius r, then the distance from here to here is on the order of e to the r. So this is sort of this is sort of the opposite of this. And this fact over here was that the fact that we used over here was that if x is negatively curved and I have two geodesics that start at points that are 1 apart, and then I draw geodesics coming in like this, then those geodesics converge exponentially quickly. The reverse of that is that if I take a point and I shoot out two geodesic rays, one here and one here, then the distance from here to here is going to grow exponentially quickly. So this turns out to be equivalent to these conditions on the Dane function. And then for all x such that g acts geometrically on x, x has what are called thin triangles. And what this is, what I mean when I say that x has thin triangles, I mean that for all x, y, and z in x, any 3 points, any 3 vertices of a triangle, if I draw geodesics from x to y and y to z and x to z, then the geodesic, let's call it gamma sub x comma y, from x to y stays in the delta neighborhood. I need a quantifier. So there exists delta greater than 0 such that for all x, y, and z in x, the geodesic gamma stays in the delta neighborhood of the geodesic from x to, let's see, I said x to y, so from x to z union x to y, y to z. So what we're saying is that if we have 3 points in our space and we draw a triangle with those 3 vertices, then each edge of that triangle stays within a delta neighborhood of the other 2 edges. So if I draw the neighborhood around around the geodesic from x to z of radius delta, and the neighborhood around the geodesic from y to z of radius delta, and then the geodesic from x to y stays in that delta neighborhood. And this is specifically what does not happen in the plane. In the plane, you can have you have triangles like this that are very thick, where if I draw a neighborhood of one edge and a neighborhood of the other edge, then the third edge only lies in that neighborhood near the endpoints. This condition is the opposite of that. It says that if I have a triangle where, say, I have x, y, and z, and if I draw the edge from x to z and the edge from y to z, then the third edge in the triangle, the edge from x to y, has to stay in the union of the delta neighborhood of the other 2 edges. So in this case, if my triangle starts out like this, then the only way to finish my triangle is for the geodesic from x to y to basically go like this. It has to stay close to the other 2 edges. And so in this case, oops, let me grab another piece of chalk. In this case, we say x is delta hyperbolic. And what this is a coarse negative curvature condition. It's coarse because it's a coarse condition because it doesn't rely on anything infinitesimal. It's a coarse condition because it really only depends on the geometry above scale delta. And it's a negative curvature condition because, well, basically because this is something that's satisfied in manifolds with pinched negative curvature. Is this okay? Is the statement of the theorem clear? Yeah?
For the fourth point, X doesn't have to be simply connected.
For the fourth one, yeah, it doesn't have to be simply connected. Because we can define this, even if X is, say a graph, we can define this notion. Right? We can define the notion of geodesics, we can define the notion of a neighborhood of a geodesic, and we can ask that for any 3 points and any 3 geodesics between those points that this condition is satisfied. Yeah?
Can we relate delta with the perpendicular curvature when it's negatively curved?
Yeah, and so you should be able to, because the way you prove that a negatively curved space satisfies this is you use various comparison theorems. So the delta that works, if you know kappa, then the delta that works for X is going to be the same delta as the delta that works for the model space of negative curvature kappa. Okay? More questions?
What means of the finitely presented group?
Finitely presented groups. So a group is a group is finitely generated if it has a finite generating set. But every finitely generated group is a quotient of a free group by some normal subgroup. And so finitely presented means that that normal subgroup is finitely generated as a normal subgroup. What that means is, so you see group presentations like this. So the group Z2 is generated by X and Y such that X, the commutator of X and Y is the identity. If you can write a group in terms of a presentation like this, where the presentation only has finitely many relators, then it's finitely presented, because each of these relators is a generator of the kernel of the homomorphism from the free group. More questions? Yeah?
Having a linear main function is the same as having a constant
Yeah.
growth.
Yeah. But having a Dane function, having a Dane function that's equal to 0 is a very strong condition. That you pretty much have to be a tree in that case. And so there are groups that act on, say, the hyperbolic plane, but don't act on trees. Is it okay? More questions? So yeah, the power of this theorem, the important thing about this theorem is that these two conditions are clearly quasi-isometry invariant, or at least we've proven that they're not hard to prove that these are QI invariant. This condition and this condition, it's not clear at all that these are quasi-isometry invariant, but because of this theorem, this theorem tells us that these two conditions are also quasi-isometry invariant. So, in particular, what makes this theorem important is that it tells us that being negatively curved, a space being negatively curved or not, is a quasi-isometry invariant, that we can actually define negative curvature just in terms of this condition, that a lot of the property, and really a lot of the properties of negatively curved spaces, a lot of the quantitative properties of negatively curved spaces really just follow from this coarse condition. So is this okay so far? Yeah.
Only for you need the complexity of the unit that every space which has a finite presented.
Yeah. So having a finitely presented group acting on you is not difficult, because if you have a if you have a simply connected space and a geometric group action, then the group that does the acting is finally presented.
Do any negative Laker space have a compact action?
No, I mean you can certainly have spaces that satisfy this that don't have any periodicity. You could just take say the hyperbolic.
Is that true that
It's still quasi-symmetry invariant.
curve is quasi-isometric invariant?
Yeah, it's still I may be wrong in some pathological cases, but but apart from it should be true. I don't know. Yeah, you might need some mild conditions like being a geodesic metric space or or properness or something like that. But it should be true in wide generality. So tomorrow we'll talk about asymptotic cones. A fifth condition that I could add to this is that a space is hyperbolic if and only if the asymptotic cone is all the asymptotic cones are real trees, and that condition is quasi-isometry invariant, and it doesn't involve the group action at all. Okay. Is this okay? Okay. So there's this very close connection between small Dane functions and negative curvature and there's this very close connection between linear Dane functions and negative curvature. We can ask if there are similar connections between, say, quadratic Dane functions and non-positive curvature, or between larger Dane functions and other curvature conditions. But in general, the answer is no. In general, we have that delta hyperbolicity is equivalent to linear Dane function. We have that a non-positive curvature implies at most quadratic Dane function. But in general, and the reverse is not true. There are a lot there are many groups with quadratic Dane function that aren't negatively that aren't non-positively curved. That aren't non-positively curved. So, for instance, there are nilpotent groups with quadratic Dane functions. There are solvable groups with quadratic Dane functions. There are arithmetic groups with quadratic Dane functions. There are many examples of groups that have quadratic Dane functions. So we have this very close link in the case of negative curvature, but the class of groups that have quadratic Dane functions is much richer. There are a lot of them, and it's hard to say what properties they have in common besides having quadratic Dane function. And if we leave linear and quadratic entirely, if we look at groups in general, there are a wide variety of possible Dane functions. So, for example, for every alpha, every natural number alpha, there exists a nilpotent group G, such that the Dane function of G is on the order of L to the alpha. In fact, for a dense set of alphas in the interval from 2 to infinity, there exist groups G such that the Dane function of G is on the order of L to the alpha. And this covers all the possible polynomial growths, because remember, there's nothing between 1 and 2. If alpha is between 1 and 2, if the Dane function is bounded by L to the alpha for alpha between 1 and 2, then it has to in fact be linear by this theorem that's behind this board. So for a dense set of alpha, we can get Dane functions of order alpha. There are larger Dane functions for many solvable groups. Have Dane functions that are exponential. We can go higher than that. There's a group with 2 generators and 2 relators, such that for all n, the Dane function of G is bigger than or equal to e to the n times e to the L. So this is a tower of exponentials of height L. This is an L times iterated exponential. So there's a group with 2 generators and 2 relations such that for all n, the Dane function is bigger than an n times iterated exponential. And if you allow for even more complicated groups, there is what?
What is the condition in the theorem with the square violated by this last example?
The last theorem was for groups. This last one? Yes, I finally presented. It has 2 generators and 2. Because Gromov's theorem says that if it has a linear Dane function, if it has a subquadratic Dane function, then it in fact has a linear Dane function, right? So Gromov's theorem it characterizes groups with negative curvature. This is a group that does not have negative curvature. Is it okay? Okay. And we can go further with this. The Dane function, it turns out, so I defined the Dane function in a very geometric way, but you can also define it in a very combinatorial way. And if you define the Dane function combinatorially, it's very closely connected to the question of, if I give you a presentation of a group and a product of generators of that group, can you determine whether that product of generators represents the identity or not? This is called the word problem. This is one of the classic algorithmic problems about groups. And like most algorithmic problems about groups, it's unsolvable. There's no algorithm to solve it. And as a consequence of that, there's a group G with unsolvable word problem I really should say for any group G, with unsolvable word problem, the Dane function of G is greater than or equal to any computable function of L. So we have a very broad range. On the low end, we know that if a group has negative curvature, if a group is delta hyperbolic in this sense of Gromov, then the Dane function is linear. But on the upper end, we have groups where the Dane function is larger than any function that we can write down.
Can you remind me what the word problem is?
So the word problem is an algorithmic problem where the input is a presentation of a group and a product of generators of that group. And the output is yes, if that word is true, if that product of generators is equal to the identity, and no if it's not equal to the identity. And this is an unsolvable, this is equivalent to the halting problem. There is no algorithm that can solve this problem. And because of that, there's no there's a group where there's no algorithm that can compute the Dane function of that group. Okay. So yeah, so there's a very wide range of possibilities from linear at the low end to uncomputable at the high end. What I want to do today is talk about a particular another phenomenon that happens in with the Dane function is that, well, we have a bound. We know that if x is non-positively curved, then the Dane function is bounded by a quadratic function. But it turns out that subsets of non-positively curved spaces can have much stranger behavior. If you take a subspace of a non-positively curved space, it can have much stranger behavior, and that behavior really comes from the non-positive curvature. And so what I want to do today is give you an example of that. This is one of my favorite examples. The example is a pair of solvable groups called Sol3 and Sol5. The subscripts just denote the dimension. So this is a 3-dimensional Lie group. This is a 5-dimensional Lie group. Sol3 is the group of matrices. It's a group of 3 by 3 matrices with e to the t, e to the minus t, and 1 along the diagonal, and with x and y above the diagonal, and with zeros in the other places, under the condition that x, y, and t are reals. So this is a 3-dimensional Lie group. You can check that it's solvable. And the Dane function of this group is exponential. Sol5 is a group that contains Sol3. It's a group of 4 by 4 matrices. And I'm going to write it like this. I'm going to put e to the t1, e to the t2, e to the t3, and 0 along the diagonal. I'm going to put x, y, and z above the diagonal, and I'm going to put zeros in all the other places. I still have this condition that x, y, z, and t sub I are real. And then I want, you'll notice here that the determinant of all these matrices is 1. E to the t times e to the minus t times 1 is 1. I want the same condition here. E to the t1 times e to the t2 times e to the t3, times 1 is 1. So I'm going to put the condition t1 plus t2 plus t3 is equal to 0. Was that, someone sounded like I made a mistake. Was that the mistake I made? Okay. So this is Sol5. This is a 5-dimensional Lie group, and the Dane function of Sol5. So Sol3 was exponential. Sol5 turns out is quadratic. And so what I want to do today is try to explain why this happens. Is this okay? Are there any questions so far? Can you see the? Sorry, I ran out of room on the board. Can you see what? Can you see what's? Okay. So let's start. So let's start by looking at with Sol3. So Sol3 is a 3-dimensional Lie group. Why does this have an exponentially large Dane function? Well, so first, let's put a metric on Sol3. Let's put a left invariant metric. And our left invariant metric is this And there's a choice to be made here, and there are infinitely many different left invariant metrics depending on choosing some norm on the tangent space at the identity. But all of those different left invariant metrics are by Lipschitz equivalent, are equivalent up to a constant. And so because all those left invariant metrics are by Lipschitz equivalent, they're only going to change the filling area function by a multiplicative constant. I've chosen this particular left invariant metric, but any other left invariant metric would give us the same answer for the Dane function up to some constants. And what if I give Sol3 this metric, then what does it look like? What is the geometry of this space? So I'm going to draw a picture of this space. So because this is a three-dimensional Lie group, we've got three coefficients x, y, and t. So I can identify it with R3, with Euclidean space, and I can ask, okay, if I take 2 points in Euclidean space, say I have 2 points that only differ in their x-coordinate, what does the geodesic between these 2 points look like? Well, if we look at this metric, the metric in the length of vectors in the x direction depends on the t-coordinate. When the t-coordinate is large, then the length of vectors in the x direction is small. When the t-coordinate is negative, then the length of vectors in the x direction gets very large. So if I want to find the shortest path from here to here, then the shortest path ends up being something roughly like this. I want to go up a certain distance in the t direction. I want to go across parallel to the x-axis and then back down. And if I do that, if this length is L, and if this length is L, and if this curve has length 1, then the distance from here to here, if I just went along the xy plane, then this length here would be on the order of e to the L, right? And the same thing is going to apply if instead of moving in the x direction, if I want to move in the y direction, then the same thing happens. Because of this e to the 2t factor on the y coordinate of my metric, vectors in the y direction are going to be particularly long when t is large. They're going to be particularly short when t is negative. And so if I want to move from here to here, then the most efficient way to do that is to go down in the t direction, back in the y direction, and then back up in the t direction. And again, if I go a distance L in the t direction and the distance 1 in the y direction and then distance L in the t direction again, and that's going to change the y coordinate by on the order of e to the L, right? And now, what if I want to move in the x direction and the y direction? If I want to go from here to here, well, the geodesics like that are going to be combinations of geodesics in the x direction and geodesics in the y direction. So if I want to look at the geodesic between this point and this point, it looks roughly like this. It looks roughly like the curve I've drawn on the board already. Or, well, if I move in the x direction and then the y direction, I end up there. But I could also reverse those two steps. I could first move in the y direction to get there, right, down, back, and up. And then I can move in the x direction up, over, and down to get another curve of about the same length that also connects these 2 points. So I have two approximate geodesics, one that goes like this and one that goes like this, right? And so these form a loop. And if you draw these with the measurements I have here, with going up and down L each time and going over by 1 each time, this is a loop of length, I guess 8L plus 4. And then the filling area of this loop turns out to be exponentially large. Because what you can do, the way you can show that it's exponentially large is you can look at the intersections here, 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 and here with the xy plane. And let's draw this parallelogram here, this square here. This is a square with sides of length e to the L. And if you examine this metric, the projection from Sol3 to the xy plane, the projection to the xy plane, let's call it P, and this is going to send xy t to xy, is area decreasing. Is area decreasing because, well, as t changes, the x direction grows and shrinks, and the y direction grows and shrinks. But as t changes, as the x direction gets smaller, the y direction gets bigger. As the y direction gets smaller, the x direction gets bigger. And so those are going to cancel out. And so when we project to the xy plane, that projection is area decreasing. And in particular, if I take if this is my curve gamma, if I have some disk beta whose boundary is gamma, then the projection of beta to the xy plane is going to be a disk whose boundary is this exponentially large square. And so the filling area of gamma is going to be at least the filling area in the plane of the projection of gamma. And this filling area is at least, well, I guess we know what it is because this is the plane, is equal to e to the 2L. And so the filling area of gamma has to be at least the area of this square, has to be at least e to the 2L. Right? So this is an argument for why the this is an argument for why the Dane function of Sol3 is at least exponential. But somehow this has to not work in the case of Sol5. Something changes between dimension 3 and dimension 5, where this curve still exists in Sol5 because Sol3 is a subgroup of Sol5. This curve still exists in Sol5, but it doesn't have the same filling area. Instead, it only has quadratic filling area. And it turns out that that one reason why has to do with non-positive curvature, has to do with the fact that we can embed Sol3 and Sol5 into non-positively curved spaces. So is this okay so far? Are there any questions about Sol3?
Can you explain why the filling area in the plane is exponential to A? In the plane, that's just the planar metric.
Yeah, so in the plane, when t equals 0, this is when we just have the standard metric on the plane.
Yes.
Uh-huh.
Projection is the unit square.
Well, no, it's not the unit square because the change in the x coordinate from here to here is e to the L. That's why we went up distance L and then over 1 and then down. Yeah, so it projects to not the unit square but the square of side length e to the L. More questions? Okay. So what changes between Sol3 and Sol5? Like I said, the easiest way to see what changes is to view Sol3 and Sol5 as subsets of non-positively curved spaces. So where do these non-positively curved spaces come from? Well, Sol3 here, this is a group of 3 by 3 matrices with e to the t, e to the minus t1 along the diagonal, x and y above the diagonal. This is a subset of the group of 3 by 3 matrices where instead of having e to the t, e to the minus t along the diagonal, I replace t and minus t with a and b, like so. And if you look at matrices like this, if you look at the multiplication on matrices of this form, then really we can think of this as two separate 2 by 2 matrices. We can write this as this, the group of matrices like this is isomorphic to the group of matrices of the form e to the a x 0, 1 cross with the group of matrices of the form e to the b y 0, 1. And these are two-dimensional Lie groups. And we can and just like we put a left invariant metric on Sol 3, we can put a left invariant metric on these two groups. We can put a metric, say dg squared is equal to e to the minus 2a dx squared plus dA squared over 2, and e to the minus 2b dy squared plus db squared over 2. So we put a metric on this product, which looks like this. And if we do that, this induces the previous metric. On Sol 3. Because in Sol 3, we replace A with T, we replace B with minus T, and you can check that if we do that, if we replace E with T and A with T and B with minus T, then we get the same metric that we saw before. So we can view Sol 3 as a subset of this four-dimensional Lie group, and this four-dimensional Lie group each of these pieces here is isomorphic to is isometric to the hyperbolic plane. This group of 2 by 2 matrices is isometric to this group of 2 by 2 matrices is isometric to the hyperbolic plane. So we can view Sol 3 as a subset of a non-positively curved space, namely the product of the hyperbolic plane with itself. Oops. And then we can ask, how does this affect the geometry? So the way that this affects the geometry, so the hyperbolic plane is negatively curved. So the hyperbolic plane satisfies this theorem of Gromov that we saw earlier. So in particular, the hyperbolic plane has thin triangles. In particular, the geodesics in the hyperbolic plane diverge exponentially quickly. Because the geodesics in the hyperbolic plane diverge exponentially quickly, one thing we can say about the geometry of the hyperbolic plane is that if I have 2 points x and y in the hyperbolic plane, and I draw the geodesic between them, then that geodesic is essentially the only short path between x and y. What do I mean by that? I mean that if I take the midpoint of x and y here, and if I draw, let's say this length is r, and if I draw a circle around the midpoint of radius r over 2, then any curve from x to y that avoids the circle of radius r over 2, any curve like this, has to be exponentially long. Because of this exponential divergence, any curve from x to y that avoids this disk, this neighborhood of the midpoint of x and y, has to be exponentially long. And this is really a property of negatively curved spaces. That in a negatively curved space, there is essentially only one essentially only one short path from one point to another. I remember we said before that that negatively curved spaces have thin triangles. Well, a consequence of having thin triangles is that if I try to go from x to y, by instead of taking the, if I try to replace the geodesic from x to y with a broken geodesic that goes from x to z to y, that broken geodesic is going to be very close to my original geodesic. It's going to look something like this. So if I have any short path from x to y that's not the geodesic, then it has to involve a lot of backtracking. It has to, if I have any short path from x to y that's not the geodesic, then it has to at least stay very close to the geodesic for most of its run. So there's essentially only one short path between any 2 points in the hyperbolic plane. And the same thing happens in the product H2 cross H2, except really in one dimension up. It turns out that instead of there being essentially a unique short path between any 2 points, in the product H2 cross H2, there are a lot of curves where there's essentially only one small disk whose boundary is that curve. So let's see this. So the property of H2 cross H2, so H2 cross H2 is not negatively curved anymore. H2 cross H2 is non-positively curved. And the reason it's non-positively curved is because if I take a geodesic in H2, and I take a geodesic in the other factor of H2, and I take their product, that's going to be isometric to R2. In fact, this is what's called a flat. And we no longer have this property in H2 cross H2, because if I take one of these flats, if I take the product of gamma and lambda, and if I take 2 points in this plane, x and y, now there are going to be paths, well, there's a geodesic from x to y that just goes straight along the plane, but there's also a path from here to here and a path from here to here where maybe the geodesic has length r, and this path has length at most, say, 3r, and this path has length, say, at most 3r. So these are not as short as the geodesic, but they're not exponentially longer than the geodesic. They're about the same length. And so there's no longer a unique path from x to y because there are these flats, but now we have these closed curves here. So this is a closed curve that lies entirely in a flat that has essentially a unique small filling. So there's an obvious filling of this curve, namely, this is a closed curve inside a plane that lies inside H2 cross H2. So it's filled by a disk, a round disk like this. But it turns out that that is essentially the only small filling of that curve. If I take the center of this disk, and if I imagine a ball of radius, say, r/2 around this, around this center, then any disk that fills this curve and avoids that ball, well, it's either going to have to make an exponentially long detour in one factor, or it's going to have to make an exponentially long detour in the other factor. Either way, any disk whose boundary is this curve that avoids a ball of radius r/2 around the center has to be exponentially large. So this is essentially the only disk of length less than of area less than exponential in R whose boundary is this curve. Is this clear? So in order to show that the filling area of Sol3, the filling area function of Sol3 is exponentially large, it would suffice to find some picture like this inside Sol3. It would suffice to find some picture like this where you have to fill some curve that lies inside a flat without using the actual inside of that flat. So let's try to find something like this inside Sol3. So this picture came from looking at a product of geodesics where we had one geodesic in one factor and one geodesic in the other factor, and we took their product and we got a plane. So what do these geodesics look like in our picture when we're writing these hyperbolic planes as groups of 2 by 2 matrices? Where we're writing these hyperbolic planes as matrices of the form e to the a x0, 1 and e to the b y0, 1. Well, here let's write out the XA plane. Remember our metric on the XA plane was that dd squared is equal to e to the minus 2a dx squared plus dA squared over 2. And so, by the same argument that we saw before in Sol 3, the geodesics from 2 points that are separated along the x-axis are going to look like this. Right? When A is large, then the x vectors become exponentially smaller. And so if I want the shortest possible path from here to here, that's going to go up and then over and then back down. And then if I extend this to an infinite geodesic, it turns out that all my geodesics basically look either like this, they go up, hit a maximum, and then come back down, or they're vertical lines. And these are all the geodesics in the XA plane. The same thing in the YB plane. In the YB plane, my geodesics are also curves, either vertical lines or curves that go up in the B direction and then hit a maximum and then come back down. And so, in particular, so what's going to happen if I take a curve like this and cross it with a curve like this? Well, let's try to draw a picture of the entire product. So I'm going to draw a picture of the AB plane. And I'm going to think of, I want to think of this as, I want to think about the projection from my entire space to this AB plane. So above each point in the AB plane, I have an XY plane. And the geodesics in each factor like this, I have geodesics in the AX plane that start down here, go up in the A direction, and then come back with a different X coordinate. I have geodesics here in the YB plane that start out here, go up in the B direction, and then come back down with a different Y coordinate. Right? Is the picture clear so far? Okay, so where does Sol 3 fit in here? So Sol 3, remember, is the set of matrices where the A coordinate is equal to minus the B coordinate. So if we take the entire space and project it to the AB plane, that's going to lie above this diagonal line, A equals minus B. And if I take one geodesic in each factor like this, and I take their product, I get a flat. And the projection of that flat to this plane, well, so suppose this is my flat. It's a copy of the plane. And then I'm going to project it to, this is going to be a product of, say, this geodesic and this geodesic. And I'm going to project it to the AB plane. So what happens? Well, this plane is going to be folded over in the Y direction, because our geodesic in the Y direction goes up and then back. It's going to be folded over in the X direction, because my geodesic in the X direction goes out and then back. And so it's going to be so my plane is going to be folded, and it's going to lie it's going to lie somewhere around here. I guess to match my drawing, I should have drawn my geodesics a little bit smaller, but you get the idea. And then we can ask, okay, if I have a flat that projects to this folded flat here in the AB plane, then I can ask, where does that intersect Sol 3? Where does that intersect this diagonal line? Well, it's going to intersect this diagonal line along a line like this. So if I just cut along that line, that should tell me where my flat intersects Sol 3. And it turns out that my flat intersects Sol 3 in a picture almost exactly like that. So that means that I've got a closed curve, namely the boundary of this diamond, that lies entirely in Sol 3. And if you do the calculations, this is almost exactly the curve that we saw before, that went up and down and then up and down. If you do the calculations, this is almost exactly the curve we saw before. And if I take a filling of this curve, well, if I were allowed to use H2 cross H2, if I were allowed to fill this curve into H2 cross H2, I would have a small quadratic filling, namely this piece that I cut out. But this piece that I cut out does not lie in Sol 3. This piece that I cut out, I mean, it lies far away from Sol 3 for most of it. And so if I have a filling of this curve that lies entirely in Sol 3, then that's a filling of this curve that avoids some ball around the center of the flat, because the center of the flat was right here. So that means that that means that we really do have a copy of this picture inside Sol 3. Namely, we have some flat in H2 cross H2 that intersects Sol 3 in a circle, where the center of that circle lies away from Sol 3. And so any filling of that circle in Sol 3 has to have exponentially large filling area. And so the Dane function of Sol 3 has to be at least on the order of an exponential. Is this okay so far? So in particular, so that tells us why Sol 3 has this exponentially large Dane function. What happens in Sol 5? Why does it become quadratic in Sol 5? Well, we can do essentially the same analysis in Sol 5. Sol 3 was contained in H2 cross H2. Sol 5 is going to be contained in H2 cross H2 cross H2. 3 copies. And now that means that Sol 5 is going to have, instead of 2-dimensional flats, Sol 5 is going to have 3-dimensional flats. If I add on one more geodesic, call it, I don't know, beta, then I get something isometric to R3. And because it has 3-dimensional flats, that means that this picture here is really contained in something 3-dimensional. And now I no longer have this property that and because this is now contained in something 3-dimensional, I can find a filling of this curve that avoids this ball, but is still sub-exponential. Namely, I can just take this hemisphere coming out of the board, or the other hemisphere, opposite hemisphere, going into the board. That's going to avoid a ball around the center, and it's still going to have the same boundary. And so that's exactly what happens over here. Instead of having flats that are products of 2 geodesics, we have flats that are products of 3 geodesics. So we add one more dimension to this picture. Instead of having an AB plane, we have an ABC space. Instead of Sol 3 intersecting the AB plane, or the projection of Sol 3 being a diagonal line in the AB plane, the projection of Sol 5 is a diagonal plane in R3, namely the plane where A plus B plus C is equal to 0. And so when we do this same picture in Sol 3, so in R3, we now have, instead of a 2-dimensional flat that's folded into quarters, we have a 3-dimensional flat that's folded into eighths. Right? It's folded along the xy plane and the yz plane and the xz plane into eighths. We cut along using that diagonal plane and unfold, and now we have an octahedron in R3. And now that curve here, that diamond we saw before, is now an equator of the octahedron. So there's a diamond going around the octahedron, and now there is an obvious way to fill that. There's an obvious way to fill that curve by a disk that wasn't there before. Namely, we can just take one hemisphere of the octahedron or the other hemisphere of the octahedron. So the reason that the curve that was difficult to fill in Sol 3 is not difficult to fill in Sol 5 has to do with the fact that Sol 3 is contained in H2 cross H2, a non-positively curved space of rank 2, and Sol 5 is contained in H2 cross H2 cross H2, a non-positively curved space of rank 3. And so what you'll find is that they're going to be, well, yeah, so the curves in Sol 5 have quadratic filling area because you have that extra dimension to work with. Is this okay so far? On the other hand, what's going to happen in Sol 5? Well, Sol 5 no longer has exponential, or no longer has an exponential Dane function, but we can generalize the Dane function to higher dimensions as well. We can look at spheres in a space and ask about the minimum size of balls with boundary equal to that sphere. And then, well, now we take this 3-dimensional flat, we fold it over itself, we cut, we unfold to get an octahedron. that octahedron is going to lie entirely in Sol 5, and it's going to be exponentially difficult to fill in Sol 5. So Sol 3 has exponential Dane function. Sol 5 has what's called an exponential second-order Dane function. It means that there are two-dimensional spheres that are exponentially difficult to fill by three-dimensional balls, and so on and so forth. If I go up to a seven-dimensional solvable group, then I'm going to have three spheres that are exponentially difficult to fill, and so on. Okay. Is this okay so far? Are there any questions so far? Okay. So there are various ways to generalize this, which are.
You can say if you know that all the higher dimensional Dane functions are bounded by quadratic.
Is there something you can say then? I don't know. So there are certainly conditions that imply that. If a group is something called automatic, then that implies that all the higher order Dane functions are not quite quadratic, because remember in Rn you have spheres with surface area r to the n minus 1 that have volume r to the n. But if a group is what's called automatic, then all spheres have filling inequalities that are the same order as in Euclidean space. I don't know whether it goes the other way around. I guess the sort of thing you would conjecture is that if you have a space where you have the right higher order filling inequalities in every dimension, that in fact the space is what's called combable or bicombable, which is to say that for any point in the space, so there's a base point where for any point in the space, you can draw a line to that base point such that if I take two nearby points, those lines are close together. That's something that's automatically true in non-positively curved spaces because you can just use geodesics. But it's also true in some spaces that aren't non-positively curved. Yeah, it would be a natural conjecture to make. I don't know whether it's true. More questions? Okay. So yeah, so there are various ways that you can generalize this. There are various ways that you can generalize this. There's a theorem of Cornulier and Tessera, which says that if G is a, I think you need, I don't remember, I think you can actually do this in a little further generality, maybe with number fields, but at least if G is a solvable Lie group, then either there exists some n such that the Dane function of G is bounded by a polynomial of order n, or the Dane function of G is exponential, and there's an algorithm. There's a calculation. There are two obstructions where if they vanish, then it has to be polynomial, and if they don't vanish, then it has to be exponential. So there's a theorem of Cornulier and Tessera that says that every solvable V group has either polynomial or exponential Dane function, and and they give a way to decide which is which. It's open. It's an open question to generalize this to higher dimensions. So this is one direction. You can, instead of looking at just these particular solvable groups, you can look at arbitrary solvable groups. Another direction you can generalize this. Like I said, one of the big reasons why this works, one of the big reasons why the Dane function of Sol3 is exponential and the Dane function of Sol5 is quadratic, is because Sol3 is contained in this rank 2 non-positively curved space, and Sol5 is contained in this rank 3 non-positively curved space. So another way to generalize this is to look at certain subsets of other non-positively curved spaces. In particular, non-compact symmetric spaces are non-positively curved, and let me say so. In general, arithmetic groups for example, matrix groups like SLN over the integers. An arithmetic group such as SLN acts on non-positively curved symmetric spaces. For example, SLNZ acts on the non-positively curved symmetric space SLNR modulo SON. And so if this action were co-compact, then this would in fact be this would be a geometric action of SLN. If this action were co-compact, sorry, let me say this differently. The thing is that this action is not co-compact. If it were co-compact, then we would know that SLNZ is quasi-symmetric to this non-positively curved symmetric space. This non-positively curved symmetric space is non-positively curved, complete, and simply connected. So it has so by the arguments from before, if this were a co-compact action, then this would be then SLNZ would have quadratic Dane function automatically. But the action of SLNZ on this symmetric space, and in general the action of a lattice on the corresponding symmetric space, is not generally co-compact. And so what that means is that, well, basically, so in this case, what happens is that the quotient, let's call this space X, and let's call this lattice gamma. In this case, the quotient X mod gamma looks something like, well, it has a cusp. It looks something like this. This is a bad, it looks, what I want to say is that the quotient X mod gamma has a cusp, and that cusp can be very complicated. The quotient X mod gamma looks roughly like, in this case, it looks roughly like an infinite simplex, where as you go further and further out along a simplex, the injectivity radius of the quotient gets smaller and smaller. This is related to Margulis's theorem. So since our curvatures are bounded, and since as we go further and further out, the injectivity radius is getting smaller and smaller, then different parts of this quotient look like different products with nilpotent groups, or different products with nil manifolds. And so this is not a co-compact action, and so we can't apply our theorems about the invariance of the Dane function under quasi-isometry. But what we can do is we can take this quotient and we can cut off this cusp. If we cut off this cusp, then what's left is compact. And so if we take the preimage of this compact piece, what we end up with is we end up with our symmetric space minus a bunch of pieces which were the preimage of the cusp that we just removed. So we end up with some subset of a symmetric space, some subset of a non-positively curved space. And furthermore, depending on the lattice you take here and the symmetric space you take here, you can find groups that are isometric, groups that are isomorphic to Sol3 or Sol5 or various other solvable groups. You can find groups that are isometric to various solvable groups as pieces of the boundary of this set. And so in particular, a lot of the things that we saw about the solvable groups, that the Dane function depends a lot on the rank of the symmetric space that they lie in, a lot of that applies also, or at least is conjectured to apply to lattices in symmetric spaces. So there's another conjecture here due to Gromov and Thurston. That if G is a arithmetic lattice, is a lattice acting on a symmetric space X, of rank, sorry, I should say of, on a symmetric space of rank K, and if X mod G is not compact, then n spheres in G are polynomially difficult to fill, or I should say have polynomial filling volumes. If, let me get this inequality right. So if I'm in rank 2, then it should be exponential in dimension 1. If I'm in rank 3, then it should be exponential in dimension 2. So if n is less than or equal to k minus 2, and exponential filling volumes if n is equal to k minus 1. And this is known in various special cases. So I've proved some results bounding the Dane function of SLNZ when n is at least 5. There's a guy who's proved similar results when G is a lattice in the symplectic group. There are various examples of lower bounds. So for instance, this part about exponential filling volumes is known when the group is the special linear group and known in a bunch of other cases. But the general case is still open, and especially a lot of the higher dimensional cases are still open. So, okay, I think, yeah. So are there any questions about anything I've done today? Okay, so I think, so this is about all I wanted to cover today. What we'll do tomorrow, so yesterday I said that we were going to take two approaches to looking at at the large scale geometry of groups and spaces. We were going to look at the asymptotics of invariance. We want to look at how various geometric quantities grow as the scale increases, and that's what we've done here. We've looked at this Dane function and how the Dane function depends on length. What I want to do tomorrow is I want to look at the other side. We said that also we were going to look at the large-scale geometry of spaces by looking at their asymptotic cones, by looking at what happens by taking limits of those spaces as the scale gets larger and larger. And so what I want to do tomorrow is I want to talk about how this property of the gain function, this shift between dimension 3 and dimension 5, how it affects the geometry and the topology of the asymptotic cones. So we'll define asymptotic cones, we'll prove some properties, we'll prove some properties of asymptotic cones, and we'll talk about the asymptotic cones of Sol 3 and Sol 5. Okay?